You know, one of AI's biggest problems, maybe its biggest dirty secret, is its massive appetite for energy. But what if we could make AI 3 times faster using the exact same hardware we have today? Well, a fascinating research paper just laid out a blueprint for how to do exactly that. So here's what we're going to cover. First, we'll get a handle on just how big this efficiency problem is. Then, we'll dive into 2 really clever ideas that researchers combined in a totally new way. We're going to look at how they found the system's true bottleneck, the absolutely surprising results they found, and then wrap up with 5 practical rules for building way more efficient AI. All right, first up, the AI efficiency problem. Look, we're all constantly building bigger and bigger AI models, but that's creating this huge headache for developers and, the data centers that have to power the whole shebang. And just to put a number on this, get this. The source material points out that a single large model needs about 3 terabytes of memory just for its short-term memory, its key value cache. That is an absolutely insane amount of data to be juggling at once. So this all boils down to the million-dollar question, right? We all want AI that's more powerful and more capable, but how do we get there without needing a dedicated power plan for every single model? How do we make this whole thing sustainable? So, what's the solution? Well, this research is all about combining 2 really clever techniques. Now, these ideas have been floating around for a bit, but this paper is the first to really model how they work together to find that perfect, efficient balance. Okay, idea number 1 is something called quantization, using a format called FP4. Think of it like this. Instead of writing out a long, super detailed number, you just use a smart, compact summary of it. Yeah, it's an approximation, but it's tiny and it's way, way faster to process. It's a huge memory saver. Idea number 2 is called structured sparsity, and this is just brilliant. You actually poke a predictable pattern of holes, basically zeros, into the data. It's like Swiss cheese. And because the hardware knows the pattern, it knows exactly where the gaps are, and it can just leap right over them. And boom, you've pretty much doubled your processing speed. So like I said, these ideas have existed separately. The real kicker here, the secret sauce, is putting them together. This is the first time anyone has built a single model that really gets how shrinking the numbers and poking holes in the data interact with each other, especially when you have a limited power budget. So how does this model actually work? Well, it's all about finding the weakest link in the chain, the system's bottleneck. Is the problem the raw computing power, the engine? Or is it the memory that's feeding data into it, the fuel line? In this old saying, it hits the nail on the head. A whole AI system can only run as fast as its slowest part. I mean, who cares how fast your processor is if it's just sitting around twiddling its thumbs, waiting for data from memory? And the model itself is actually beautifully simple. First, it figures out the absolute maximum speed of the compute engine. Then, it calculates the max speed of that memory fuel line. And the true achievable speed, it's what's called the harmonic mean of those two, which is just a fancy mathematical way of saying it's always going to be limited by whichever one is slower. Right, so the endgame here isn't just about raw speed, it's about efficiency. The model is built to hunt for that perfect sweet spot, the combination of settings that gives you the absolute highest throughput per watt, the most bang for your buck for every single watt of energy you use, all while staying inside your power and speed limits. So what happened when they actually ran this thing? The model found the ideal settings for peak efficiency. And the results, well, they are seriously counterintuitive. Not what you'd expect at all. First off, to get the absolute best efficiency, the model says you have to crank that FP4 speed up all the way to the max. We're talking a full 8x performance boost from shrinking those numbers. Second, you also have to be super aggressive with the sparsity. The best results came from poking holes in 75% of the data. That means for every 4 pieces of information, you're literally just throwing 3 of them out. But this is the real jaw-dropper. To hit that peak efficiency, the system should only use 0.1% of its available computing power. Yes, you heard me right, 0.1%. I mean, that sounds completely backwards, doesn't it? It's like building a Formula One engine and then telling the driver they can only let it idle in the pit lane. Why on earth would using such a tiny fraction of its power be the key to winning the race? Well, here's the wild reason why. It's because that compute engine, which is already supercharged by that 8x FP4 speedup, becomes the massive bottleneck in the system. It's so ridiculously powerful that trying to run it any faster would just blow right past your energy budget. So by throttling it way, way down, you save an incredible amount of energy, but you're still delivering incredibly high throughput. And this table from the paper makes the pattern crystal clear. Just look at the top configurations. It's the same recipe every single time. Max out the FP4 speed up to 8x, use that high 75% sparsity, and then that same unbelievably low compute utilization of 0.1%.
Okay, so let's get to the payoff. What does all this mean for actually building the next generation of AI? Well, the paper boils it all down into 5 clear, totally actionable rules.
So here it is, the blueprint. First, you max out the acceleration you get from FP4. Then you use really aggressive sparsity. But the absolute key, the big insight, is rule number 3. You have to throttle that compute engine way, way down to save power. And then for things like chatbots, use small batch sizes to keep things responsive. And finally, of course, make your models smaller to begin with. And when you actually follow this blueprint, the gains are just huge. The data shows FP4 by itself can give you about a 3x boost. Sparsity can then double that. But by optimizing them together, the way this model shows you how, you get these compounding benefits that push performance even further. And remember, this is all on the exact same hardware. And that leaves us with a really provocative final thought. This stuff isn't just about saving a few bucks on an electricity bill in a data center. It is about unlocking entirely new capabilities. I mean, what could you build if the most powerful AI models could run efficiently on your phone or your laptop? What new frontiers could we explore if we could build even bigger, more powerful models and still stay within today's power limits? That is the incredibly exciting future this kind of work helps build.